Let's talk about how to interpret the sensitivity report for our Lego problem. The most valuable information is usually the sensitivity report section for constraints, but you also get some useful information for the variable cells. For each of our decision variables, tables and chairs, there is a row. And what this tells us is how much we could change our objective coefficient. So that's our profit margin for this problem. How much our profit margin could change without changing the optimal solution of 2 tables and 2 chairs. You can only take these one at a time. You can only change it for one, either tables or chairs. You can't change them simultaneously and for this to be valid. But let's say we're changing the profit of only chairs. Change profit of only chairs. Okay, it is $19. $19 is our base case. What this is saying is that 2 tables, 2 chairs remains optimal if our profit per chair is between 19 minus 3.5, so that's $15.5, so it could go down by $3.50. It can go up by $12 and 31. So it went up by $12 here. As long as our profit per chair is in that range, we're going to have 2 tables and 2 chairs as our optimal solution. If it drops below that range or above that range, then we need to resolve. So what's going to happen is if it drops below 15.5, you're going to build build as many tables as possible, and if it goes above this range, then you're going to build as many chairs as possible. And you saw that in our class problem, in our exercise 8A problem, it went up by $23. So our profit per chair went from $19 to $42 when the selling price went from $37 to $60. That led to 4 chairs and 0 tables as the optimal solution. So that's how we would interpret this allowable increase and allowable decrease of our objective coefficient. For the constraints, the interpretation is what we would pay to break even on each one of our constraints. This is what's known as the shadow price, and it's used in a lot of applications in a lot of different ways. The simplest interpretation is how much you would pay for an additional unit of the constraint. For labor, how much will we pay for labor? Well, from the exercise, you told me hopefully that it was 0, and that's true. You would pay $0 for labor. And that is fine as long as you go down to, as long as you drop to 10. Labor can go up to infinity, so that's 1e to the 10 to the 30th, that's just infinity. And it can go down to 10 before we start having problems. If it drops to 10 and you're thinking about going from 10 to 9, then you would need to resolve this, and the different calculation might be in play. For the small blocks, you should have told me that you'd pay $7 extra dollars beyond whatever you're paying normally for the small blocks. You should pay $7 extra for 2 small blocks, which is $3.50 per block, and that's fine as long as you are talking about increasing by 2. We're increasing by 2, or we're actually getting rid of 2 small blocks. So if we were selling off small blocks, we would be willing to sell them as long as we get at least $3.50 back. And with large blocks, they are worth $12 to us. We'd be willing to pay $12 for 1 large block, or sell 2 small blocks or 2 large blocks for $12 each. So that's how you would interpret these constraints. We would use the word non-binding for a labor constraint because the shadow price is 0, and it has a positive shadow price, or if it has a non-zero shadow price, those constraints are going to be binding. Let's talk about a revenue management problem that makes use of sensitivity analysis. Let's say we're the dorm for a 100-room hotel with customers buying at $199 per night or $299 per night, and that's either for a 1-night or a 2-night length of stay. We have a forecast for Wednesday through Saturday, and we already have sold some rooms for each night. So how many reservations should we accept from each combination of the rate class and the length of stay if we want to maximize our revenue? Our variable is going to be xijk. So we have 3 subscripts here, three dimensions to this variable, with I being the rate, and convention is we just use numbers to index it. So rate 1 is equal to $199 per night, and rate 2 is equal to $299 per night. We have 4 days when the reservations start. Day 1 is equal to Wednesday. Day 2 is equal to Thursday, and etc. for Friday and Saturday, being 3 and 4 respectively. And then LOS, we're using our length of stay dimension as using the variable k, and for what we're going to have here is that for LOS1, that's going to equal a 1-night stay, and LOS2, so k equals 2, is equal to a 2-night stay. We have our objective function. We're going to have 2 rates, 4 days, 2 length of stays. So 2 times 4 times 2 is 16. So we have 16 variables. And each one of those variables represents a specific customer class accepted at a specific rate for a specific number of nights. So we have our 4 variables for customers who are accepted at the $199 price for 1 night. These are the 4 different days at which the reservation can start. We have customers who start on those 4 days but stay for 2 nights, so we get 2 times $199 from them. $299 from customers who start on each of those 4 days, and 2 times $299 for the customers who start on each of those 4 days and stay for 2 days. So these are our variables. This is our objective function. What are our constraints? We need to make sure that demand for each of our 16 rate, day, length of stay combinations does not exceed our forecast. We can't sell more than 100 rooms for each of our 4 nights that we're studying. We only have a 100-room hotel. Also, we can't go negative in the number of rooms we're selling. We can't buy rooms from a customer class so we can provide more than 100 rooms to other customer classes. That is not possible. And that's actually going to be assumed by Solver. It will say assume that non-negative variables are assume that unconstrained variables are non-negative. And so we don't need to do anything special for that, but we should write that out as one of our constraints. Let's see how to formulate this in Excel and solve this problem.